So we talked about convergent plate boundaries where tectonic plates come together, divergent plate boundaries where they pull apart. And the last type to talk about are transform plate boundaries, where they grind past one another. Now the most famous example of this will be the San Andreas Fault out in California. This is where we have one major plate, the Pacific plate, sliding past another major plate, which is the North American plate. And the line that delineates the two is called the San Andreas Fault. Now, this type of plate boundary is a plane. So three-dimensionally, it's a plane going down into the ground. It can be curved, but it's a plane that goes down a depth where one side slides past another side. And it's just that simple. So in this case, with the Pacific plate riding north relative to the North American plate, what that does is it moves these pieces of land to the west of the fault from about San Francisco down into the Baja slowly north. And so sometimes you'll read jokes like, oh, Western California is going to slide into the sea, that sort of thing. And that's not true. That's never going to happen. What will happen over time is that this piece of land will ride north, and if you were to stay alive for 5 or 10 million years, LA will be off the coast of San Francisco at some point as this rides north.
So soon Tijuana is going to be in the United States?
Yeah, so soon Tijuana will be in the United States. Right, not the move.
Oh wait, but it's probably not as fun.
Yeah, that's fun.
Alright, I'm not, for real, if that's San Andreas Fault, that movie, would it actually just be a big tsunami that would just
No, not really. Not in this particular case. Well, that's not entirely true. Let me show you.
Okay.
So this is what the San Andreas Fault looks like, where it outcrops the surface. It doesn't outcrop the surface everywhere, but it does in places. Where the left-hand side is the Pacific plate, and the right-hand side is the North American plate, and you have that fault zone going three-dimensionally down into the ground. Now, the fault zone itself moves. So if you kind of back up a little bit and look at it from an aerial perspective, you can see where things have moved over time. So this is an example right here. You've got Pacific plate, North American plate, fault zone itself right here. And what will happen is that things like rivers and drainages will slowly get offset over time. In this case, it's by quite a bit. In this case up here, where the fault zone's running about like that, it's offset just a little bit. This will also happen with things that are built. So, like this, curbs and things like that. In this case, this particular curve where the fault zone comes across like this is the Pacific plate, this is the North American plate. It's slowly moving as fast as your fingernail grows. And fault zones are either locked up and not moving at all. Then when they do move, it generates an earthquake and you get movement at one time, or it creeps along very slowly.
Why is the San Andreas Fault so active though, compared to?
It's not so active compared to other faults, but it's because there's so much energy involved in moving these big tectonic plates.
So that's why.
So it's a constant sort of process. There's a lot of energy being released all the time along the fault zone.
What prevents them from going under each other? Since they're two different, one's a oceanic plate, one's a.
Because you're changing the forces. You're moving them sideways relative to each other, so there's no vertical offset. They're just going side to side.
So it's just direction?
Just direction.
Okay.
Right. Just direction.
I always thought that happened because the tree roots were growing.
Not in that case. But yeah, certainly. In areas where infrastructure has been built, if the fault is moving, you'll see that offset over time. Where it's locked up, you'll see it in one fell swoop, which causes a lot of damage. Now, it's not as easy as that, though, because these types of faults are not just a single plane, a single fault plane in the ground extending for miles. They tend to be segmented like branches to a tree. So this particular graphic right here this is San Francisco, so this is California up here, this is the Pacific Ocean down there. The main trunk of the fault runs up like this, past San Francisco, and then continues on and goes out to sea. But in reality, there are segments moving off the main trunk of the fault, and like branches to a tree, some are big, some are small, and all of these move at a different rate. So if you kind of map these out a little bit in terms of, this is the same thing, this is San Francisco, California, so north is that direction right there. The main fault zone coming across right here, and then all the different segments that have been mapped out, they each move at a different rate. Some are constantly moving as we sit here very slowly, as fast as your fingernail grows. Others get locked up due to friction. And when they get locked up, the friction works on those areas and eventually causes it to crack because the forces moving it are continuous. The stars you see here represent the most recent earthquakes. This isn't the best graphic in the world, but there are some dates here when segments moved. And the bigger the star, the bigger the earthquake. So the 1906 earthquake, which was a big one in San Francisco that caused fires that took out the city and resulted in the formation of fire departments around the country. And others in through here. Each one is a known quantity and is mapped out, and a lot of work is done trying to understand, is it locked up, is it moving? If it is locked up, when's it going to break? And when it does break, how bad will it be? And when we talk more about earthquakes, we'll talk about this. The most recent one here was in through here back during the World Series back in 1988, is that right? I was watching that show actually when it happened. It was kind of cool. But so anyhow, these tend to be segmented, they move at different rates. And we'll come back to this when we talk about earthquakes. But around the world, this color right here represents where all the transform plate boundaries are relative to big tectonic plates on the planet. So North American plate, Caribbean plate, which is small, African plate, Eurasian plate, Indian, Australian, Pacific, and so on. Some of these are divergent plate boundaries, some are convergent, and where they slide past one another, like the San Andreas Fault, that's a transform plate boundary.
So how, like with the Scotia plate, like since it's so small, how does that like not go underneath like one of the big plates like this?
It does. This is where the South Sandwich Islands are. So there's a subduction zone right here, where the Atlantic is being consumed right here and right here. It is all a space-saving measure. You've got the globe, which stays fixed in size, and these plates moving around. So yeah, some are consumed, some grow, some slide past one another.
So is the San Andreas Fault like the biggest transform boundary like along like
Yeah, I think so. One of the biggest, for sure. And the best in terms of how much research has been done with it.
Are tsunamis usually caused by earthquakes?
I'm not sure what the percentage would be, but you've got earthquakes, number one, underwater landslides as well, and
Which is kind of like an earthquake, right?
kind of like an earthquake, but it's a water displacement.
Yeah.
So earthquakes, underwater landslides, and underwater volcanic eruptions, like the one that occurred in Tonga this past year.
So has it ever happened that a place got hit with an earthquake and then a tsunami after because of?
Oh yeah, absolutely.
That's
Some of the
tough.
biggest, most damaging tsunamis that occurred around the world. The 64 Anchorage one, for example, up here, which devastated Anchorage, was a big earthquake.
Was this tsunami like 1,000 feet tall or something?
No, I don't think we'll see that unless you have an asteroid come in.
Wasn't there like a big one in Alaska that was like a big wave on
That's
it?
the one that
The worst one in recent times was down off of where am I? Sumatra.
So how tall a tsunami is just like how tall is like a regular sized tsunami?
A tsunami is we'll talk about when we talk about oceans, we'll talk about waves.
Okay.
A tsunami is a wave with an abnormal wave length, and there's no definition for size. A tsunami might be 2 feet tall, 30 feet tall.
So we've probably got hit by a tsunami.
Right. It's just an abnormal wavelength. So, I mean, it might not be a danger whatsoever at all. Or in the case of the one in 2004, they came into Sumatra, they killed 500,000 people. That's a severe danger.
So a tsunami hit Virginia Beach. Well, I don't know if it's good.
It
But,
could
like,
easily, sure.
Yeah, so like tsunami hits Virginia Beach. Would it affect us here?
No.
Doesn't it like go up the rivers or something though?
No, if you're watching a movie like Deep Impact, then yeah, but not so much.
There's like a movie about that one, wasn't there?
Yeah.
What was that called?
Yeah,
San
Deep
Andreas.
Impact, I think, maybe, right?
There's one where like they're on vacation and
An asteroid
2012?
comes in, hits, and generates.
no, it wasn't an
this giant
asteroid. It
thing.
was like there's a family on vacation.
Yeah, then they start running.
Yeah.
I watched that
Yeah,
one.
dude. Oh, I've
You
seen
can
that.
try, you can try to run.
That was like Transformers then.
Right, so divergent plate boundaries, transform plate boundaries, convergent plate boundaries. There's one last piece of plate tectonics, though, that we need to talk about. Something called a mantle plume. So back when we were talking about convergent plate boundaries, where you have subducting oceanic crust, which is heavy and dense, going down beneath either more oceanic crust or continental crust, I talked a bit about how when it gets down to around 100 kilometers, it partially melts. Now we'll get into this in great gory detail in a couple of weeks. But it only partially melts, because it doesn't get hot enough to melt everything. So it partially melts, it generates a little bit of magma that rises to the surface to form new continental crust, or what I call popcorn-style volcanoes like Mount St. Helens or Mount Fuji or something like that. But the rest of the downgoing slab continues to work its way down, all the way down to about the core mantle boundary, where it does get hot enough to completely melt. That creates what's called a plume. And that plume is less dense than the surrounding mantle, and because it's less dense than the surrounding mantle, it works its way back up to the surface. Yeah.
Wait, so with the Yellowstone type of deal, why is it like that there is so much like activity there compared to like anywhere else?
Because of this, because you're generating a plume of magma that contains a lot more volume than what you're generating right here. This is popcorn style volcanism because you only have a little bit of magma. This is nuclear bomb style magnetism, where you've got a huge amount of volume of material rising back up, and when it reaches the surface, it forms what's called a hotspot.
If that volcano erupts in Yellowstone, is it gonna kill like everyone?
No.
And is that hot spot? That's where the what's it called? Basalt.
Hotspot is where this mantle plume reaches the Earth's surface and then comes out.
And what comes out is basalt, like when it cools.
Yeah, depends on where you are. So this, for example, Hawaii. Let's talk about Hawaii. Hawaii represents one of Earth's hotspots, where a plume of magma is coming up and releasing a gigantic volume at the surface. And in this case, it's built up a series of islands over a very long period of time. This is the Big Island of Hawaii. The Big Island sits on top of an active mantle plume. That's Mauna Kea. It's got snow on top. Yes, you can go snow skiing, boarding in Hawaii. They might get
That's
50,
so cool.
60, 100 inches of snow a year up where the telescopes are. It's really cool.
Is that a lot?
How tall is that?
it's
No, but
normal.
it doesn't ever melt.
13,
Right?
3.
Are you
It does melt in the summer.
Or like melt in the winter, like it just keeps
yeah,
the
oh yeah,
snow
it'll
that
melt
it
in the
has.
winter sometimes. It's
Oh,
not like
okay.
snow pack the way you might have in the Rockies. But Mauna Kea is Hawaiian for White Mountain. And so that tells you how common it is there. So if you ever read some article or something, somebody trying to debunk climate change or whatever, saying, "Oh my God, it snowed in Hawaii," how
Yeah.
That's
It
because
always
you're,
does.
they're either stupid or they're trying to, everybody thinks of Hawaii as, palm trees and warm water, but it snows there just like anywhere else.
You got mountains.
And horses. But anyhow, let's talk about a hotspot and what it does with respect to Hawaii. So, a hotspot, again, is that huge plume of magma rising up from the core mantle boundary, and it reaches the Earth's surface and it comes out to form, a huge volcanic eruption. Hotspots, for the most part, are fixed relative to the mantle and the center of the planet. Now, on top of that, you have Earth's crust, and the crust is moving around, just like we got done talking about. This stuff is moving around, about as fast as your fingernail grows. So in the case of Hawaii, in the Pacific Ocean, you've got this hot spot that's fixed in location, and you've got the Earth's crust on top of it, moving along about as fast as your fingernail grows. When one of these plumes is very active, in the case of a hot spot that's on top coming through oceanic crust, it forms a rock like basalt, called basalt. And basalt is pretty heavy and pretty dense. It's this stuff again, It also forms a type of volcano that is not very explosive. This stuff, when it comes out on Earth's surface, forms a lava flow coming down the side of the volcano. You can get pretty close to it. You can take helicopter flights over it, that sort of thing. There's a lot of gas, poisonous gas, and things like that. It's released, and it's very hot. So it's still dangerous in that respect. That's not explosive like some volcanoes are. Yeah.
So when a volcano explodes and there's like ash in the sky and stuff, does that ever come down, or is it like onto the ground, or is it sort of
Talk
just?
about that in a
Oh,
minute.
yeah.
But in this case, it's just lava flow on top of lava flow on top of lava flow. So what happens is that it builds up over time, and because there's so much material coming up through these hot spots, you can form, over a relatively short geological period of time, a big island. And so that's what's happening with the island of Hawaii today. These are separated in time by about 600,000 years. And so you get this big plume of magma, comes up to the Earth's surface, comes out as lava flow on top of lava flow, and it takes about 500,000 years to expend itself. Do you have a question?
Yeah, so Hawaii is just like a big lava flow, keep coming out. So
One after the other.
So how does it get dirt?
How does it get to be dirt? All right, well, hang on, we'll get there. I'll get there. So in the case of the Big Island today, if you age date the rocks, everything is less than about, 500,000 or something like that. And it's a big, active, still growing island. As you move away, work your way to the west, because this plate is moving in this direction. If you look at the islands like Maui, Molokai, Oahu, Kauai, the islands do a couple of things. Number one, if you age date them, they are all separated in time, again, by about 500,000 years or so. And they get smaller. Because this type of rock, the salt, to answer your question, weathers very quickly. For reasons we'll talk about later in the semester. Water and oxygen knock this back very quickly compared to something like granite. And because the Hawaiian Islands are so wet in places, Kauai gets on the order of 400 inches of rainfall a year. This stuff weathers away very quickly. The islands get quite small as you work your way west, because again, it's like a treadmill, all the islands moving along here. When you get west of Kauai, and they kind of disappear beneath the surface and become what are called seamounts, all the way out to Midway and Kear Islands, where they disappear underneath the surface.
So is there gonna be like another like big island like that's gonna come up
Yeah.
after?
It's called Luihi, and it's about 5,000 years from breaking the surface.
And is it, and as Hawaii's gonna shift, it's gonna
And-
stop growing,
yep,
and
it'll
then
stop growing.
Okay.
So as that new one in 5,000 years pops up, will the other ones like the Midway Islands go down?
Yeah, they probably will wear beneath the surface of the waves.
It's like I'm sure there's civilizations.
Hotspots are stationary sources of magma within
Yeah.
Earth's mantle. Magma rises through oceanic crust, which is moving over the hotspot. Eruption of magma forms a volcanic island, which moves away from its hotspot source along with the oceanic crust. This process is then repeated.
So there you go. Sometimes it helps to see this visually.
The hotspot responsible for the Hawaiian Islands has been in existence for over 80 million years. resulting in a long line of volcanic islands extending from the extreme northern Pacific Ocean to Hawaii. The bend in this line was caused by the Pacific Plate changing directions approximately 45 million years ago. Each island and seamount in this long chain formed from innumerable volcanic eruptions, only to become extinct as it moved away from the source. Present-day volcanic activity is restricted to Hawaii's Big Island and a nearby seamount named Loihi. Loihi will eventually grow large enough to become the newest island in this long volcanic chain.
Alright.
So when that new, when Loihi pops up, there's not gonna be any natural dirt on it, right?
No, but because it's like the rock weathers very quickly, it only takes a matter of years, if that, before it can form soils.
Do you think that we'll add soil to it?
I think the number is actually more like 50,000 years.
So it's
You
gonna
think
be a while.
human civilization will still be around by then?
Yeah, it'll be gone in a couple years.
Nah,
anyways.
but-
Yeah, I mean,
Because of that, just the way it forms as a soil, like, does that have anything to do with how, like, trees and how objects can, like, grow there? Because, like, there's a lot of palm trees and stuff like that, because
Yeah.
they can grow in that weird
this type
rocky
of soil, this type of rock is extremely nutrient rich. And because it weathers to soil very quickly, it gets taken over by life within a matter of a year or two after a big
Oh, wow.
deposit. I mean, it happens very quickly.
Okay.
So these are the Hawaiian Islands, right? You've got the Big Island, Maui, Molokai, Oahu, Kauai, and so forth. When you zoom into this area right here, and again, this is the current activity. Mauna Loa and Kilauea are down here. Kilauea has been the longest continuously active volcano on the planet. It's been going now for 40 years without stopping. Mauna Kea is above. There's been historical activity there, as well as on Maui. And I think there's been historical activity on Oahu, but just barely. Again, you move off, the islands get smaller. They're about 500,000 year or so, about 500,000 years apart in their ages, if you age date them. And they work your way all the way across the Hawaiian Islands to Midway and Cure, where some of the World War II activity was located in through there. And then beyond that, they become seamounts where they have disappeared beneath the surface of the waves, and they are seamounts that technically you can dive down to. And those seamounts get smaller and smaller and smaller, and again, the ages get older and older until everything is subducted down into the Aleutian Trench way up in Alaska.
So you said with like the wave, like we're talking about waves later, but like how come some waves on some? I know like it has to deal with like reefs and stuff, but like
Okay.
why are some like bigger on like some sides of Hawaii?
Because of that, because
see.
you've got ocean currents and weather patterns generating swells, in a predominant areas, and then you have the underwater topography, which has a huge effect on what the actual wave will do. So if you have a reef out here, you're not gonna have big waves. Kind of like if you go to Virginia Beach or something and there's a big sandbar out there, that's gonna trip the waves.
Yeah, so it makes them die.
Yeah, it makes them die. That's what reefs tend to do.
Yeah.
Yeah. If there's nothing like that there, you can have a big swell coming on shore.
Gotcha.
So because basalts weather so quickly, and we'll come back to this a little bit, there's a couple of things with respect to these types of islands, not just the Hawaiian Islands, but basaltic oceanic islands in particular. One is the type of sand tends to be the black or green or tan in color. If you go to Waikiki and it's a beautiful white sand beach, that's because they barged that sand in from Florida and dumped it there. Same is true for like Sandbridge or Virginia Beach. Sandbridge, that's all fake sand. They spent $21 million back in 2019 replenishing that for the 6th time.
Holy crap.
It's a nice place.
Nice place, but the beaches are fake.
But like OBX, like they're real because it's like
Yeah.
shelly. And,
Yep. Yeah, we'll talk a lot about that later on this semester. But one of the reasons why we like the Hawaiian Islands so much from an aesthetic standpoint is because they weather so quickly, they get so much rain that it does this. It gives you these little knife edge ridges and things like that that people sign. It's very pretty. So you want to go to Hawaii, you want to go to French Palm Beach, and those kinds of places because of this. You know. Now, around the world, there are a number of hotspots. Not just the Hawaiian Islands. The Hawaiian Islands are the best example of a hotspot in terms of explaining it and understanding how it works. But these are the number of hotspots around the world. Some of them come up in oceans, like the Hawaiian Islands. And that gives you basaltic, non-explosive kinds of eruptions. There's one beneath Iceland, which is why Iceland is a divergent plate boundary with a hotspot beneath it, which means there's so much stuff that's built up at the surface that you have formed a big island. And a few others out in the oceans, but there are some on the continents as well. And those are completely different. They work the same as a hotspot. You've got crust moving overneath, and you get these periods of volcanism separated in time by about 600,000 years each. But the end result of it is quite different. And when we talk about volcanoes, we're going to go over this in a lot more detail, but just suffice it to say that magma that comes up through continental crust is different than when it comes up through oceanic crust. It makes the volcanoes much more explosive and dangerous. We'll talk about why. So in this case, yeah.
Wait, are you gonna go to the what are the calderas?
All right, well in this case, a good example of a hotspot coming up through continental crust is Yellowstone. It's the one we're most familiar with. The type of volcano that results from an eruption, a hotspot eruption on a continent, is called a caldera. That's different from Hawaii. So Mauna Kea, Mauna Loa, the big island of Hawaii, is Earth's largest mountain. 30-some odd thousand feet tall from its base to its summit. Not tallest, but largest. On the other hand, when this type of stuff comes up beneath continental crust, because it generates a volcano that behaves differently, because the material is different, you end up with a big explosive eruption and then a hole in the ground afterwards. And that's completely different. It's exactly the opposite from like the big island of Hawaii. Because of that, this wasn't well understood for a long period of time. It wasn't even recognized for what it actually is for a long period of time. But beneath Yellowstone National Park is a hotspot where material comes up, separated in time by about 500,000 years, 600,000 years. It's expended during a big eruption, then it quiets down, and the crust moves off that hotspot. And in this case, the current hotspot is beneath the national park. And if you trace out where the North American plate, the direction it's moving right here, you can follow previous eruptions down the Snake River Plain in Idaho. If you age date, then you get about a 600,000 year period between big eruptions. Now beneath Yellowstone National Park, we zoom in a little bit. Yellowstone National Park, if you've been there, it looks a bit like this. Wyoming, Idaho, Montana. It's a big national park, obviously. And when you are inside most of the park, you're actually inside the rim of the volcano. This volcano is about 60 miles across. Now think about this for a minute. When you think of like Mount St. Helens or Mount Fuji or something like that, a volcano that forms a mountaintop, there might be a little caldera at the very top. That might be a few hundred yards wide or something like that, where magma comes out, lava comes out. This one is 60 miles across. That's the mouth of the volcano. It's quite large. It's also quite active. Let me zoom in on this a little bit. Just to give you a little bit of perspective. This is Yellowstone National Park right here. So it's about yay big. It's quite large, and when it goes off, it puts a lot of material out into the atmosphere. And when it's done, it collapses like deflating a balloon and forms a depression in the ground. And that depression now, if I back up a little bit, is basically what Yellowstone National Park is. Yellowstone Lake, this is a closed system here. The water has nowhere to go. So the water just sits in here, in this depression. And then you have some mountains around here, which they have, walled off now as Yellowstone National Park. It's active. There's an active hotspot. And the last time it went off was 630,000 years ago.
Ooh.
Before that was 1.2, before that was 1.8, which makes you think.
We're due. We're due for
Yeah,
one.
we are. We're majorly due for a gigantic eruption.
Mm.
But
That'd be cool.
this is the difference between YouTube and something out there on the internet. Because yes, I'm expecting this thing to erupt sometime in the next 50 to 100,000 years.
What?
I'll be alive for this though.
Don't hold your breath.
Why don't we just drill straight down and relieve some pressure?
We'll come back to that.
Because we don't want
Boom,
to
boom,
die.
boom. Just another.
Well, we'd be chilling, wouldn't we?
We'll come back to that because
No,
nature did that a little while ago, and I'll show you what happened.
Would it reach us?
Yeah.
Yes, of course.
Would it?
But here's the difference in time scales, though. This is where geologic time interferes with human time and sensationalism. Yes, we're overdue. No, this is not going to happen in your lifetime or probably the lifetime of our civilization.
Can you guarantee that?
Yeah,
Why?
because it takes a long time to come up to speed. This size volcano, as opposed to a smaller volcano like Mount St. Helens, which we monitor and can see coming for a couple of years in advance, because this is so big, it's going to take probably a few hundred years to come up to speed, if not more. And there will be so many signs of this happening that we will know it way in
Come
advance.
up to speed as in coming up to the Earth's surface.
Yeah, stuff getting close to the Earth's surface and building up to a point that's going to actually do something.
What would be some hints?
We'll talk about that when we get into volcanoes.
So do you think this is gonna be like the end of the world when it goes off? Like
Not
that one movie?
entirely.
Isn't it gonna kill like
How far do
over
you
a
think
billion
it will
people?
I'll show you.
go? 2D.
But I just want to point out, though, that this is a fun thing to talk about because it does so much damage.
Nice.
But, and it can be sensationalized because it's active and because there's a lot of stuff going on here, a lot of earthquakes, a lot of ground swelling with the lake moving around, minor volcanic eruptions. Because of that, it can be sensationalized. You can read stuff all day long on the internet about how we're all screwed and the government's keeping you, from knowing the truth, and we're all going to be wiped by Yellowstone. Not true. Because you got geologic time working here, and yes, I would expect it in 50 to 100,000 years, but not anytime soon. What it does is it releases a lot of material into the atmosphere.
Dang.
There may or may not be an explosive, shock wave associated with it. There will be locally. But it releases a lot of what's called ash into the atmosphere. And that ash is a lot different than a lava flow, the kind you might see coming down the Hawaiian Islands. It releases a huge amount of volume into the atmosphere. And this is the dangerous part because ash is actually little pieces of glass, not ash, and a lot of poisonous gas. And that stuff accumulates, and when it accumulates, it's hot. It's about 2,000 degrees Fahrenheit, a little less than that when it accumulates. So it melts whatever it falls onto. But it's quite big. So for example, the last major eruption we had in the lower 48 was 1980 Mount St. Helens, 0.25 cubic kilometers worth of material. The last time Yellowstone went off, 1,000 to 2,000 cubic kilometers worth of material. So it puts a lot of stuff into the atmosphere. And it covers a lot of ground. So for example, anything inside here is basically not survivable.
Oh, Yellowstone?
Yeah.
Why won't we go more north?
In terms of, being able to live there after the eruption and that sort of thing.
Doesn't it like cover the sun?
Why wouldn't you go more north?
That was kind of the winds. This is just where the last
I got
few
it.
eruptions fell.
Okay.
So like, could be a massive like tsunami from that though?
No. There might
Is
be a
it
little
too
bit of a
far
shock
away?
wave. locally in terms of it exploding or something, but mostly you're talking about hot, deep ash accumulating and smothering the area.
So
Doesn't it like cover the sun too? So it's
Oh,
just
yeah.
be pitch black
I heard
everywhere
it's
under
maybe
that
like 3
area.
years we go and see the sun or
So
something.
how?
Now, there hasn't been a recent example of this. So all we can do is look at the geological record and say, wow, measure it. We can look at what it's done to life in the past. You can go to Nebraska to a place called Ash Fall Park, where during the last eruption, animals were simply stopped in their tracks and covered by something on the order of 40 to 50 feet of ash. It's really cool to see. I mean, it's kind of morbid, but it's kind of cool to see what happened from a scientific standpoint.
Isn't that just like Pompeii?
It's like Pompeii but on a grand scale, yeah, absolutely.
Oh, Pompeii wasn't that big.
This is
Pompeii was small.
I have it on video.
But you might look at this one, Toba, 74,000 years ago. We're going to come back and talk about volcanoes in more detail.
Volcanoes
This
are
is
what?
just kind of an intro. This is a sensationalistic intro, by the way. Don't be going home and saying we're all doomed because of Yellowstone.
We're not doing
I will.
This geology teacher tells me we're all going to be wiped out. That's not what I'm trying to say. But 74,000 years ago in Indonesia, there was one of these eruptions that's called Toba. And Toba did quite a lot of damage. And you might ask, okay, so what's going to happen to civilization when Yellowstone goes? Well, one, it's not going to be good. But two, it's going to be so far in the future that it's almost pointless to even worry about it. But we do have historical precedents for what a more recent one did. So 74,000 years ago, Toba, which is down here, released enough of this stuff into the atmosphere to be comparable to Yellowstone. Now, 74,000 years ago, obviously there's no civilization like we understand it, but there were humans. And there is DNA evidence. Now, this gets well beyond my expertise. Well beyond. But there is DNA evidence that the human population back then was reduced and went through this funnel of about 5,000 or so individuals. And for a long period of time, it was not understood why the human population decreased so dramatically then to such a few number of individuals on the planet, and then it kind of populated since then. Now we understand, we link that to Toba and what it did. This is kind of a busy graphic to humans and their ability to migrate starting about 74,000 years ago. One of those reasons, though, is because of what this type of volcano does to the atmosphere. This type of volcano puts a lot of soot and ash into the atmosphere to block sunlight. It also puts a chemical compound called sulfur dioxide, SO2, into the atmosphere. The more of this you put into the atmosphere, the cooler you make the atmosphere because it reflects sunlight. And 74,000 years ago, after Toba, the Earth's average temperature went down for a very long period of time to basically ice age levels. And so you have crop failures and that sort of thing that occurs.
So that's how we solve global warming. We cause a huge eruption.
Yeah, you light off Yellowstone.
We'll just make a bunch of SO2s.
But the changes in the atmosphere that are the results from these kinds of volcanic eruptions, not just Toba, but lots of different kinds of volcanic eruptions, have resulted in migrations of humans around the globe from the archaeological and anthropological standpoint. Quite often, we'll come back to this again, talk about why. At least in terms of SO2 and what it does to the atmosphere. Earth. So yeah, okay. That is plate tectonics. That is the underlying driver of everything else we're going to talk about during this semester. Now we're going to zoom in. We're going to talk about minerals, how minerals form, what they are, what we use them for, who has what, that kind of stuff. And in the lab, you're going to identify them. But everything we go back to, you can trace into plate tectonics: divergence, convergence, transform, mantle, plume, whatever. Some of it's quite boring. In the case of hotspots, it can be quite exciting, and it can be sensationalized in the media in a way that I understand, even though it's not really reality. So, and I think from the standpoint of things we talk about this semester, when it comes to sensational stuff, I think it's important to understand the science behind what you see in the news. You can go back and read about Yellowstone and all kinds of sensational stuff, but if you don't really understand the process behind it, how are you able to look at that news article and say that's wrong? So I think it's important to understand how things work, so you can critically judge some of that stuff. And we'll do a little bit of that during this semester. Yellowstone is one. Yeah, sure, it's a big deal. It's not gonna happen in our lifetime, so it's just fun to do.
You think?
I think, yeah. No, that's, I'd put 100% of that.
Alright, I'll find you one.
It just takes, come find me one day when I'm wrong.
Yeah.
It just takes so long to come up to speed, this type of volcano. We would know it by now. No question about it. So.
I mean, if Russia gets more-
What's your favorite mineral?
I don't have a favorite mineral.
Salt?
We all